Hello, this is Mike Huner again, and I'm going to be working with you on this next session, our topic of calculating volumetric properties. Again, as a reminder, in this session, what we're talking about are these volumetric properties of our asphalt mixtures that are the important properties that we need to ensure our pavement performance. As a reminder, some of those properties can be seen here on this phase diagram. We have our compacted asphalt mixture represented by our aggregate coated with our asphalt film. When we look at that from a different perspective over here on this side, basically we break those components up. It makes it easier to visualize. So a compacted sample has a very large volume of aggregate, a much smaller volume of liquid asphalt, and then a very small volume of air voids, or what we refer to as voids total mix, VTM. Some of those other components we're going to be looking at, we've already discussed some. Voids in the mineral aggregate, which is represented as all that space in between all those aggregate particles where our asphalt and our air voids are going to fill up. Our voids filled with asphalt, what percentage of that VMA gets filled with asphalt? Let's look at what these different properties are, and we'll get into how we calculate them. So again, the properties we're interested in from a specification and a performance standpoint: voids in the total mixture, referred to as VTM, voids in the mineral aggregate, referred to as VMA, voids filled with asphalt, referred to as VFA, and then another one, a very important property of fines to asphalt ratio, FA, or what percentage of fines, the dust in the mix, for the asphalt content of the mix. Now, before we get those, there's some other important properties that we need to introduce and talk about as well. These other properties are our effective specific gravity of our aggregate. We've got a property that refers to how much absorption that aggregate or how much water absorption it has, which also gives us an idea of how much asphalt it's going to absorb. So by knowing the effective specific gravity, we can then calculate another value that we're going to need, which is our bulk specific gravity of our aggregate. And then finally, another important parameter that we're going to need is the percent binder effective. That we have our total asphalt or our total binder content, but some percentage gets sucked into the rock or absorbed by the rock. So the percentage that is left or effectively coating aggregate is important. So we're going to also have to calculate these values as well. So first of all, the effective specific gravity of the aggregate. And how do we calculate that? So this equation, if you look at what's in this equation, you may see some familiar numbers here or terms. So we have our effective specific gravity of our stone, that's what the S stands for, so GSE. And to calculate it, we start with our percent stone on top. We have a percent binder in the mix, so we simply subtract the percent binder from 100. That gives us what percent stone is in the mix. And then on the bottom of the equation, 100 over the GMM. You may remember we already talked about maximum specific gravity of the mix. That's this value here. Over here on the right side, again, our percent binder in the mix divided by the gravity of the binder. What is the specific gravity of the liquid asphalt? So if you look down here, again, we define what these different terms are that we're going to need to be able to calculate GSE. So here's an example for you to walk through. So we say that we've got a mixture that has a percent, let's start with the binder, has a percent binder in it of 5.98% liquid asphalt. So with that, we subtract the 5.98 from 100. That tells us our percent stone in the mixture. That would give us 94.02% stone. So that's the two primary components. Also, the GMM, we ran a maximum specific gravity test, and from that test, we got a value of 2.494. And then finally, because we're working with our binder is in the mix as well, we need to know the gravity of that binder. A very standard value for specific gravity of liquid asphalt is 1.03. And that's going to be pretty common till you get it to some asphalts that are either very heavily modified or have some other products in them that may change that value. So as we plug these numbers into our equation, percent stone 94.02, 100 over the GMM value, 5.98 or the percent binder divided by the gravity of the binder. We work that out, we would get an effective gravity of the stone of 2.742. An important thing to know here with the aggregate gravity, this is an aggregate property. That's why it's much higher than our mixed gravity of 2.494. This is a property of just the aggregate, not the mix, not the liquid asphalt. Now we know our effective gravity of our stone, which is going to be used in this equation here to calculate our bulk specific gravity of our stone. Okay? That's the property we definitely need, but to get here we had to first calculate the effective. Another value that you're going to need to be able to determine this bulk specific gravity of the stone is this correction factor. This correction factor is determined during the mix design procedure, during that process or that step. So on your job mix formula, you should have listed a correction factor to be able to take an effective specific gravity of the stone, make a correction or adjustment to it to determine the bulk specific gravity. So as an example, we just determined an effective gravity of 2.742. We get a correction factor from our job mix formula of 0.034. That gives us a bulk specific gravity of our stone of 2.708. We're going to need this number for some of those volumetric calculations. So back to some of our volumetrics. That most important one that we talk about a lot, the air voids in the mix. Voids in the total mixture. This was talked about back in chapter 3. But to reiterate or to remind you of what we're looking at, voids in the total mix refers to the small air void spaces or the small spaces of air that remain between the coated aggregate particles in that final compacted mix. So when it's in its compacted state, it's the air voids in and around those compacted coated aggregate particles. Air voids are important. They're necessary in dense graded highway mixes to allow for additional pavement compaction under traffic by providing a space for small amounts of asphalt binder to flow during subsequent compaction. So it gives that mixture room to breathe or to sustain loading. For most of our VDOT mixtures, typical ranges of air voids or VTM in the laboratory were somewhere usually in the neighborhood of 2 to 5% air voids. In the field, when we're compacting out on the road behind the paver with the rollers, generally our air voids are going to be higher at that point, maybe 5 to 7.5. And then we're going to expect traffic to take it back down closer to that laboratory air void range. To calculate VTM or air voids in our mix, we're going to need two important factors. We've calculated these earlier, that average bulk gravity of the mix from our compacted lab samples, as well as that maximum specific gravity of the mix. With those two values, we can determine what air voids are in that compacted sample. So again, earlier we ran those testing, we calculated those properties, an average GMB value of 2.411, an average a GMM value from the Rice gravity test of 2.494. By plugging those numbers into our equation and running through our calculation, we arrive at a VTM or an air void content of 3.3% air voids. So we're saying that that average lab compacted sample has 3.3% air voids in it. The next important property that we need, volumetric property, is the VMA, voids in the mineral aggregate. Again, we talked about this earlier in chapter 3. Voids in the mineral aggregate is that air void space that exists between aggregate particles in a compacted paving mix if we could remove all the asphalt. So we've compacted the mix and we could magically suck the asphalt out and that aggregate stays in that orientation with each other. It's all the air void spaces in and around those aggregates. It allows us space to put asphalt and to have some air voids left over. So VMA represents that space that's available to accommodate both the asphalt binder and whatever volume of air voids we're trying to obtain. The higher the VMA, the more space we have available for asphalt. That tends to increase durability. That helps us get more asphalt in for durability. So typically most specifications are going to require some minimum volume of VMA, minimum amount of VMA to make sure we can have enough asphalt in the mixture. To calculate voids in the mineral aggregate, here's our formula for that. You can see the values that we need. Again, that average bulk gravity of the mix from our compaction procedure, those 3 samples that we compact and average together. We're going to also need this PS. Again, that's the percent stone in the mix. This is a property of the aggregate skeleton, so we need the percent stone in the mix. And then also we need a gravity of that stone. That's that bulk gravity of stone that we just calculated a few minutes ago. So with those values, we're going to bring those in, these values we've been calculating. The average GMB from our 3 compacted gyratory samples, 2.411. The bulk gravity of the stone we just calculated a few moments ago of 2.708. And the percent stone in this mix, 94.02. So as we plug those numbers into our formula, walk through our calculation, we should arrive at a VMA percentage. This is an air void percentage in and around those aggregate particles with no asphalt, 16.29%. Okay? Or you could round that to 16.3. So that's our percent voids in the mineral aggregate. And then the third property, third volumetric property, another void property, is looking at a little different. Now we're looking at what percentage of those VMA voids gets filled up with asphalt, or voids filled with asphalt. It's that percentage of voids in that compacted aggregate mass, or the VMA, that gets filled with asphalt. Okay? VFA is an important, not only as a measure of durability, but it also is important because it has an excellent correlation between it and percent density. So it gives us a good relative idea of how well this mixture is going to compact. 2 different things. It's kind of a balancing act. If our VFA is too low, then that means that there's not enough asphalt binder to provide durability, and the mix will be prone to fatigue or early age durability problems. On the other side of the spectrum, if the VFA is too high, then the available VMA has been overfilled with asphalt. So we have to put in more asphalt than we really need, and then our mix can be prone to over-densification or compaction under traffic, not be very stable, not support traffic very well. So there's a balance there. Okay, so in terms of VFA, you're going to see specifications that have a minimum and a maximum, or a range that your VFA has to fall inside of. To calculate voids filled with asphalt, you see our formula here, and you see it's essentially a ratio of the VMA and the air voids, because we're trying to determine what percentage of our VMA gets filled up with asphalt. So to do that, we take our VMA, we subtract our air voids, divide that by our VMA times 100. Okay? So as an example, we earlier calculated an air void, or a VTM, of 3.3% air voids. We also calculated a VMA of 16.3%. So by plugging those numbers in, 16.3 minus the 3.3 divided by the 16.3, and we arrive at a VFA of 79.8%. So almost 80% of our VMA gets filled up with asphalt, is essentially what this is saying. So now we've determined air voids, VMA, and VFA. We've still got another important property to calculate, and that was that fines to asphalt ratio. To get to fines to asphalt ratio, we're going to have to calculate first another property that has to deal with binder absorption by the aggregate. So the term that we're interested in here that we're talking about is determining the percent binder effective. Remember, I said earlier, the percent binder effective, think about some of that asphalt gets sucked into the rock or absorbed by the rock. The rest of it is effectively coating the rocks and holding it together and giving us durability. So we want to know what percent of our binder is the effective binder. Okay? This is a pretty complicated looking formula, but again, let's look at what goes into this formula. So we're trying to determine some percentage of the binder that's coating aggregate. So that means we start out with what's the total binder percentage? Percent binder in the mix, total binder. And then as we move into our formula here a little further, percent stone. What's the percent stone? 100 minus the percent binder. The gravity of the binder, GB, remember that 1.03? And then gravity of stone effective, or effective specific gravity of the stone, we just calculated that a few minutes ago. And then we also calculated a bulk specific gravity of the stone, or the aggregate as well. So that's these numbers here. So we already have all the information we need. So if we bring those numbers into our equation, remember our percent binder was 5.98. Subtract that from 100, and that gives you the percent stone of 94.02. So that's the two percentages of the main components. And then the gravity of the binder is 1.03. The effective gravity of the stone we calculated earlier to be 2.742. And the bulk gravity of the stone we calculated a few moments ago as well. Remember, using the correction factor, and that gave us 2.708. So by plugging those numbers into our equation, it's a complicated equation, but just take it step by step, work inside parentheses first, and you should work across and arrive at a percent binder effective of 5.59. So again, what this is telling us is, although we have a total binder of 5.98, only 5.59 of that 5.98 is actually coating particles. That difference is what gets absorbed into the aggregate. It's not used, essentially it's wasted if you want to think of it that way. So the more absorptive our aggregate is, the bigger difference you'll have in these two numbers, the total binder and the percent binder effective. Now, we need that percent binder effective to calculate this last volumetric property that's important for durability and performance. And that's that fines to asphalt ratio, FA. Okay? It's an indication of the asphalt binder film thickness of coated particles. So it gives us an idea of durability, what kind of film thickness we have of the binder around those aggregate particles. So it's a very important property. That film thickness helps reduce, obviously, premature aging, moisture damage, durability, improved durability, or lack of durability. So it's a very important property. We calculate our fines to asphalt ratio using this formula. As it's said, or as it's described, it's the fines in the mix that we refer to as what percentage of our gradation is passing the number 200 screen. We typically refer to that as the percent dust in our mix. So what is the percentage of dust, or P200 material in our mix, divided by not the total binder content, but the effective binder, that binder that's coating particles and holding things together. So again, make sure the number that's being used here is that effective binder percentage. We just calculated that value, okay? So if we plug our numbers in, we look at our aggregate gradation from our testing. We determined that our percent 200, or our percent dust in the mix, is 6% dust. Our percent binder effective, we just calculated that to be 5.59 by using those two values in our formula. 6.0 divided by 5.59 brings us to a 1.073, or a 1.07 as our fines to asphalt ratio. Again, this is a ratio that gives us an idea of mixed durability, premature failures. There's typically, in specification, there's going to be a range that your fines to asphalt ratio has to fall inside of. It can't be too low, can't be too high. Okay, so a 1.07. So with that, those are the important volumetric properties that we're going to have to test for and meet those specification requirements. So again, if you've got questions, or as you work through these examples in the book, check with your proctor, ask him for help, he or her for help with any of those questions.